1. My total momentum here has to be positive 1. Because my sum has to be negative 9. I know momentum is mass times velocity, so that should be equal to 4 kilograms times whatever my velocity is. Therefore, the math problem is 1 is equal to 4v. That's the math problem. Yep. Units?
M divided second square.
Ooh. You went too far.
MS square. MS divided by S square. Second square.
You keep going too far. Drop the last word. It's not squared.
Meters per second.
Meters per second. Second squared, meters over second squared is acceleration.
It's acceleration. I'm sorry.
Yeah, no problem. All right, and it's positive. I don't have to technically write the positive, but just emphasizing the fact that it is a vector. It is going to the right because we said to the right was positive. All right, some fun with numbers. All right, so we started out with this guy over here. So I had the 5 kilogram mass, and I had the 4 kilogram mass. So it'd be 4 and after. So the 5 kilogram mass starts out with 15 Descartes. And the 4 kilogram starts out with negative 24 Descartes. Afterwards, the 5 kilogram mass now has negative 10 Descartes. And the 4 kilogram mass is 1 Descartes. So this is just recapping what we've already done. What is the change in momentum for the 5 kilogram mass?
D and the first 5 kilogram 5D. The change is 5D.
Now I'm looking for an actual number, not a formula.
$25.
Close. Verbally close. Numerically.
Negative 25? Negative 25?
Yep, negative 25. It's the difference. It's the final minus initial. It's negative 10 minus 15. What is the change in momentum of the 4 kilogram mass?
Negative 23.
You added them.
Minus 25.
No, close. It's final minus the initial.
25.
Yes, 25. Positive 25. 1 minus negative 24. This is 1 minus negative 24. And this is negative 15 minus 10. So negative 25 Descartes of impulse was applied to the 5 kilogram mass. Positive 25 Descartes was applied to the 4 kilogram mass. The fact that they are opposites, when you add them together, you get 0 because the total change in the whole system is 0. But there was impulse applied to each. Momentum did change for each object, but the total stayed the same. Questions to hear? Okay, remember there's that one formula I want you to have memorized and be able to recite. with enthusiasm would be a really nice bonus. In unison. I'm about to ask for that. Here we go. What's the formula for kinetic energy?
1/2 mv squared.
Sort of doing that in rounds, sort of an echo kind of thing. All right, so we have 1/2 mv squared. Let's see, let's get rid of some stuff. I need that. Want to keep that. Don't need that anymore. Don't need that. All right. So the kinetic energy of the 5 kilogram mass, as you just said, 1/2 mv squared, so it's 1/2 times 5 times 3 squared, which is what? Is it 67.5? Only the 3 is squared.
Is it 22.5?
That makes more sense. Yeah, please make sure that you know how to do this on your calculator. The biggest mistakes I see are people multiplying 5 times 3 first and then squaring, or multiplying 1/2 times 5 times 3 and then squaring. Do recognize only the 3 is squared. What are the units here? 22.5 what?
G.
And you said?
D.
No, that'd be for momentum.
G.
Is it J? Joules. It's the joule. All right, so the kinetic energy of the 4 kilogram mass, 1/2 times 4 times 6 squared. Not doing -6 squared, even though that would give you the same answer, but it's the speed squared.
G.
So my initial kinetic energy in the system is what? Are you stopping there?
Joules.
There's more to it than that. That's definitely in there, but don't forget.
Negative.
Oh, no, not an issue with that. I've got 2 different objects here.
94.
Yeah, it's the sum. So 94.5
Yes.
joules. All right, so that's before the collision happens. I've got this amount of energy. Let's do it for afterwards. So the kinetic energy of the 5 kilogram mass afterwards, final. So 1/2 times the mass times the speed squared. Yep. And then for the other one, the kinetic energy of the 4 kilogram mass final, 1/2 times its mass times that speed squared, that's 0.25 squared.
3.125.
So the final kinetic energy is
3.125.
was energy conserved in this collision?
No.
It's not the same number before and after. There's no change in it's in a straight line here. It's not like we're worried about potential energy, that there's been some change in elevation or some other force involved like that. So there's a loss. The change in kinetic energy is less than 0. This has a special name, of course. This is called an inelastic collision. Or just to confuse things, or an elastic collision. So let's talk about some vocab again, because you can never get too much. There are a couple basic types of collisions that there are certain trigger words that automatically will tell you something. So first off, in a collision, you should immediately assume momentum is conserved unless they throw in a whole bunch of other stuff. So these are collisions. Collision types. We assume P initial is equal to P final. Total. So the variation happens based upon the energy. So we're going to call this naming convention number 1. Naming convention number 2. And then Fox convention. If kinetic energy is conserved, so the change in kinetic energy is 0. Under naming convention number 1, this is called a perfectly elastic collision. Under naming convention number 2, this is called elastic collision. And I'll get to what I call it in a minute. If kinetic energy is lost, but they don't stick together, do not stick. Do not stick together. Like this situation right here. Under naming convention number 1, this is called elastic collision. Under naming convention number 2, it's called inelastic collision. And then the third situation down here, there's a loss in kinetic energy and they stick together. Under the first convention here, this is known as an inelastic collision. And under naming convention number 2, this is perfectly inelastic. Perfectly inelastic. And so the vocabulary that I use tries to eliminate any possible controversy depending upon which system you're using. So I call this perfectly inelastic here. Sorry, perfectly elastic there. I call this one perfectly inelastic here. So the perfect ones are kinetic energy is conserved, elastic, or they stick together in elastic. I didn't really have a name for the middle one, like this situation here. The student suggested imperfect, which I like. So this is imperfect. And there's there's a fourth category. So any questions here before I talk about the fourth category? In the fourth category, kinetic energy is gained in the collision. They agree on this one. You should not gain kinetic energy unless there's some explosion. There has to be some external source of energy there to cause it. So Canadian kinetic energy, they would call this impossible. And I call it Flubberesque. After the movies. Well, after the substance in The Absent-Minded Professor. I guess eventually there was a movie called Flubber. So that's why I said it's called inelastic or elastic, depending upon. In the naming convention too, they consider elastic is that if I drop the ball, it would bounce up to the exact same height. Others consider elastic as that they just bounce. All right, questions to hear. Then let's go through another exciting example. And there are specific numbers I do want to pick for this. There we go. So a 3 kilogram mass going to the right at 4 meters per second. And then I have a 9 kilogram mass going to the left. Oops, sorry, misread. A 1 kilogram mass going to the left at 6 meters per second. After the collision, the 3 kilogram mass, so this is before and after, going to the left at 1 meter per second. And the 1 kilogram mass has some final velocity. So what I would like you to do is figure out what is the final velocity of the 1 kilogram mass and what type of collision is it? We can do it together or you can do it individually, whichever way you. Are you ready to try it solo? Okay. Saw one nod and didn't see any head shakes, so why don't you try it solo?
Left or right positive?
What are you going to do?
Is to the right.
Okay. If someone has already chosen to the left to be positive, then nothing necessarily wrong with that. But will we do it as a group after you've done it as individuals? then we'll use that convention. I think it's implied, but I'll go ahead and state it formally. Assume a closed system.
So if you're saying to the right is positive, then that would be negative, because that's going to the left. And that would also be negative. All right. First question is right.
So if you're saying the change, so you're saying this type of closed system, the change in the amount which would be there, right?
The total change. Yeah. I would recommend doing the momentum thing first. Unless you've done it somewhere and I'm not seeing it. You're jumping straight into the energy. You're answering the second question first. But you're gonna get stuck in here.
Yeah.
You have to do the momentum part first. Well, check it out, didn't you? That is correct. That is not. At least you showed your work, we were able to identify it quickly. You have your total initial. So you also now have your total one. It's up one. So once you have, this one right here. So that's the total initial. That's also the total one. So you have your initial momentums here. So from that, what's the total initial? You just, when I'm talking the total initial, I'm asking just the sum of those two.
Yeah.
And that should be the sum of those two. So that's the total. That's for this. That plus something should equal that. Which would, in essence, you would be doing that, plus that. And that will be the total limit for this guy. For which you can find the velocity. Ultimately, it's the momentum of that plus the momentum of that equals that. One small thing that's going to the left. That's negative, yeah. forget, oh, sorry,
Oh.
I said myself what you were doing. Never mind.
I thought it was positive.
Alright. Good with that, how'd you get that number?
Just